Thank you, Chintan. So first of all, on this special event, Vigyan Yatra of 9 days, I welcome our Chief Patron and Honorable Vice Chancellor, Professor Nilambari Ben Dave. Equally, I am welcoming advisor of GUJCOST, Professor Narottam Sahu sir. I am welcoming today's renowned speaker, Professor Ganesan sir, and our good friend, Dr. Vishal Joshi ji. Along with that, our head of department, Professor Hirenbhai Joshi sir, all participants throughout the India. We have the participants more than 1,000 from all states of our country. So in 2020, we did this kind of organization. We had given the name Bhautik Yatra, and it was 9 days and 18 speakers spoke on a beautiful thing about the physics and technology. Again, we started this Vigyan Yatra under this Gujarat Vigyan Sammelan 2024. We have that all eminent personality throughout 9 days, and everyone who are attending, they will enjoy. They will get a lot of knowledge from these all invited speakers. So on first day, I am thankful to all invited speakers that in very short duration we requested to provide the talk, and they all are ready to provide the talk. So I am thankful to them. I am also thankful our Vigyan Bharatis and Vigyan Gurjari. Thank you, all of you, as a participant, and I am sure that you will enjoy each and every day with a new insight, new kind of topic. Thank you very much.
આપણા સૌમાં બિરાજમાન પરમ તત્વને હું પ્રણામ કરું છું. Dignitaries who have joined this event today, dear faculty members, HOD Nikesh Bhai, and all the participants. I congratulate all of you to join this event, and I heartily welcome you all on the board of this event for a continuous of 9 days. Vigyan Yatra 24 is a travel of 4 scientific Indian young minds towards Vikshit Bharat. Is a series of conferences with the journey through wonders of science that designed by considering a broad spectrum of beneficiaries, right from the undergraduate students, postgraduate students, research scholars, faculties, researchers in science and other disciplinary areas. This series is organized as a part of Gujarat Vigyan Sammelan 2024. After the grand success of Jointly Yatra 2020, a lecture series of 9 days, with the participation of 5,000 plus participants overall in the presence of Padma Shri Professor H.C. Verma, IIT Kanpur. This series is being organized with the same idea of an active interaction between resource person and learners, with a broader spectrum considering the multidisciplinary and interdisciplinary aspects of NEP 2020. Different eminent speakers, including world renowned senior scientists, faculty members, and eminent alumni friends of Saurashtra University, will be delivering their talks on their expertise area. The series deals with importance of material science, nanotechnology, which changed thinking of physicists and includes the topics from the astronomy to accelerators, neutrons to gamma radiation, terahertz to metal organic framework, magnetism to plasma physics, materials for nuclear reactors, and other recent interdisciplinary priority research areas of science, technology, engineering, mathematics, with respect to India at global level. This series of conference is scheduled during March 4 to 15, 2024, 9 days, 2 speakers on each day, and total 18 invited speakers will participate in this event. Till now, 600 plus participants from different research institutions, universities, and colleges from 18 states and 5 union territories across the country have registered for the Vigyan Yatra 2024. Also, 50% participants are from Gujarat and others are from outside the Gujarat. So, I congratulate all of you for participating in this event, and I think that will be very fruitful event for researchers and learners in the area of science. So, thanking you all for participating, and hope you will enjoy this event fully. Thanks a lot. Jai Jai Garvi Gujarat, Jai Bharat, Jai Hind.
Good afternoon, all of you. And I'm here welcoming all the dignitaries, Professor Nilambari Dave, the Vice Chancellor, sir, Saurashtra University, Dr. Sahu, sir, from the GUJCOST, Gujarat Council of Science and Technology, as well as our Registrar Sri Ramesh Bhai Parmar, and other dignitaries, Dr. and Professor Nikesh Shah, sir, and Professor Hiraj, sir, from the Department of Physics, Saurashtra University, and all the joinees who have joined the Vigyan Yatra. Let me thankful to all of you by saying a few words about the Vigyan Yatra. That we are knowing that the Vigyan, basically we are thinking that what we are doing that for the betterment of the society, and with this approach, the Vigyan Bharati have started to elaborate the Vigyan towards the all of the it can be reached from the scientists to the students who are living in the India with the knowledge of the science and technology. Sorry for these interruptions. So, as a part of this Gujarat Vigyan Sammelan, we have started the Vigyan Yatra, and in this Vigyan Yatra, all over the nations, the recognized professors and dignitaries as well as scientists are joined and deliver us a precious speech on their thoughts about the Bharat of future, or the what we will be going to be for the future. So I'm very much thankful to all the dignitaries, all the speakers who have joined, and all the
Good
students
afternoon,
as well
sir.
as faculties who have joined over here with us. I'm very much thankful for that. Thank you very much. Thank you all of you. Jai Jai Garvi Gujarat. Jai Jai Saurashtra University.
Now, am I audible to everyone? Okay, fine. So, in this session, which commences from now onwards up to I think 5:15, there are two talks. First talk will be delivered by Dr. Vishal Joshi, and next one is by Dr. V. Ganesan. So, Honorable Vice Chancellor, Madam, and present Head of the Department, Professor Nikesh Shah, and distinguished speakers for today's this session, Dr. Vishal Joshi and Dr. V. Ganesan, and coordinators Dr. David Dhruv and Chintan Panchasara. I, on behalf of Physics Department and on my personal behalf, I welcome everyone in this Vigyan Yatra, which is having more than, I think, as I'm observing on the screen, 175 yatris of Vigyan. So let us start first talk by Dr. Vishal Joshi. Before that, let me give a brief introduction of Dr. Vishal Joshi. I am very happy and feel proud to introduce Dr. Vishal Joshi, who is a renowned scientist in astronomy and astrophysics division of the Physical Research Laboratory, Ahmedabad, and alumnus of our department, Saurashtra University. Dr. Joshi earned his master's degree with gold medal in physics. As I told you, he is alumnus of this department from Saurashtra University in 2004, and then joined PRL as a research scholar. With over 17 years of experience in the field, his research interests span a wide range of topics, including observational studies of nova, supernova, and other variable stars, astronomical instrumentation, and automation in astronomical data analysis. Dr. Joshi has an impressive publication record with over 50 research papers published in reputed international journals, including one in Nature in 2015, the most prestigious journal in scientific research. He uses advanced telescopes such as the Mount Abu IR telescope, Himalayan Chandra telescope, European very large telescope, infrared telescope facility, and Hubble Space Telescope to conduct his research. He is also one of the key members working on commissioning the 2.5 M class telescope at Mount Abu Observatory, which will be the second largest telescope in India. Dr. Joshi is a member of several prestigious organizations, including the International Astronomical Union, Astronomical Society of India, Gujarat Science Academy and Gujarat Mathematics Association. Dr. Joshi is not only a distinguished researcher but also a passionate science communicator. He has delivered over 180 popular lectures and conducted more than 60 workshops on various scientific topics in astronomy, physics, and mathematics across the country. He serves as an advisor for various institutes, including Science City Ahmedabad, where he provides guidance and support to aspiring young scientists and helps to promote a culture of scientific curiosity and inquiry in the wider community. I now invite Dr. Vishal Joshi to deliver his talk on knowing the cosmo giant, that is a black hole in the center of our galaxy, Milky Way. Dr. Vishal Joshi, please. Hello.
Yeah. Am I audible clearly? I hope so. Yeah. Thank you, Professor Hiren Joshi, for introducing me. It's an honor to get introduced by one of our teachers, under whose guidance I completed my masters. And I always take opportunity to visit. This time it's a virtual visit, but in physical visit also I always take opportunity to visit the Saurashtra University Physics Department and interact with the young minds. It's my alma mater, and I always love to be there. So thank you for inviting me to deliver this talk. Professor Nilambari Ben Dave, Vice Chancellor of the Saurashtra University, Professor Nikesh Shah, the head of the department, Professor Joshi, and all other dignitaries, professors, head of the departments, and of course, all the participants. In this talk, I'm going to introduce some known and most of the unknown aspects of the black holes. And the talk will revolve around the discovery of a supermassive black hole, which the discovery has actually okay, I'm trying to share my screen, but I'm unable to. The button is disabled, so I think somebody from you, the administrator, has to allow me to present my screen. Yeah, thank you. I am able to do it now. Let me do it. Yes, I hope you can see my screen. Yeah, great. So this talk, as I said, will revolve around the discovery of what we call supermassive black hole in the center of our own galaxy. And this was the first ever direct evidence of a discovery of a black hole. This is actually a supermassive black hole, and that's why I use the word knowing a cosmo giant. How giant it is, anyway, we are going to say. So first of all, we start with what is a black hole. So black hole can be simply defined like a black hole is a region of space from which nothing, not even a ray of light, can escape. The black hole is region. Remember, it is not a body. It is a region of space. Because black hole is primarily made up of body. It's a body material. But the material is so compact, so tightly bound, we don't know of what kind of structure it is. And that's why black hole is called singularity in our universe. And that's why it is more considered a region of space than a real body. The theory of general relativity predicts that a very compact mass deforms space-time to form a black hole. I'll not go into much detail because otherwise this talk will not be that interesting and entertaining. So we'll move to some of the early historical aspects before moving to more interesting discovery aspects of these black holes. So the concept of black hole is not very new. In early 18th century, people started thinking about some of the very compact, dense, and heavy bodies which contain so immense gravitation, which even can bend the light within itself. So, English naturalist and philosopher, and also a geologist. In those days, the speciality was not there. I mean, there was no specialist. A medical doctor can pursue wonderful research in mathematics, in physics, maybe in chemistry, and also in astrophysics. So they were, jack or probably a master of all. Nowadays, we are focusing more and more in specialization. So this John Michel was a geologist, philosopher, and also English naturalist. So he wrote a letter to Henry Cavendish, a very renowned physicist, who for the first time calculated the value of capital G, that is the gravitational constant given in Newton's gravitational equation. So he wrote a letter to Henry Cavendish and gave the concept of a dark star. Apparently the stars are very bright, including our own sun. All the stars appear to be very bright. But, John Michel gave the concept of dark star, the star which absorbs all its own light. Also, the famous mathematician, the Laplace equation and Laplace theories are well known, it's on his name. He suggested in one of his books that high gravity objects may trap all the radiation emitted by itself. And not only that, he has given a very interesting comment on it, that therefore possible that the largest luminous bodies may, through this cause, be the luminous and heaviest body may be invisible to us because light cannot come in from that. Story continues, and we reaches in the modern physics era of modern physics, where Albert Einstein has given the general, special and general theory of relativity, and quantum mechanics is also under development. In that time, Professor Carl Schwarzschild, the one who solved the equations of general theory of relativity for the first time for stars, and he solved, his solutions are known as a Schwarzschild solutions, a very renowned German physicist. Carl Schwarzschild explained in the theoretical possibility of a black hole, considering general theory of relativity, in a letter to Professor Albert Einstein. So it was a private communication between Schwarzschild and Einstein, where Schwarzschild has given an idea that, give me a minute. Yes. Oh, I hope this is, yeah. Yeah. So, Albert, in a letter to Albert Einstein, he has mentioned that, according to general theory of relativity, the existence of black hole may be there. However, both of them were not sure about physical reality. Both of them had a doubt that what is called physical theoretical concept has actual physical reality. Is there a black hole in the universe? So even Albert Einstein was not sure about the existence of black hole, a prediction on his own theory. So from where this word black hole comes? The black hole actually comes, it was coined by John Archibald Wheeler late in 1960s, in 1967. So the famous word black hole was not there in the whole lifetime of Albert Einstein. Moving ahead, what is a black hole? So any object can be black hole. Any object can be shrink enough. We know the equation of gravitational equation given by Newton, that is F is equals to G m1 m2 upon r square. The force, gravitational force, acted between two objects of mass m1 and m2. Let us talk about one specific object, M1, and we calculate the gravitational potential, that the gravitational potential is proportional to mass of that object and inversely proportional to the radius of that object. Now you keep the mass same and reduce the radius, shrink the whole object. The gravitational potential on the surface of that object, if the object is getting shrunken up, will increase. So Schwarzschild was the first one who calculated a radius at which an object converts into a black hole. And that radius is called Schwarzschild radius. So Schwarzschild radius Rs is equals to simply 2 into G into M upon C square. G is a gravitational constant, C is the velocity of light, which is also a constant. M is the mass of the object. Interestingly, the word Schwarzschild in German language has a meaning black shield. And the Schwarzschild radius works as a black shield for all the radiation emitted from that star. So, you know, हम जैसे बोलते हैं ना, उन्होंने अपना नाम सार्थक किया है. Let us have some estimation of what a black hole size can be. So assume a star which is heavier than our own sun. The star with 3 times the mass of the sun need to be shrunk enough to a 9 kilometer sphere, 9 kilometer radius sphere to become a black hole. And this is the realistic number. The star with 3 solar mass will actually have radius of almost, 1 million kilometer. So you have to shrink the star almost to 100,000th time in radius and 10 to the power 15 time in volume to make it a black hole. And we have identified such 3 solar mass black hole. So you can imagine how dense these materials are. Let us increase the mass significantly. Instead of few solar mass, let's talk about few millions to a billion solar mass. So let's go to other extreme. A star cannot be of this mass, but an object of 1 billion solar mass will have very large radius, which is comparable to a Jupiter's orbit, and still it can be a black hole. So remember, if mass is sufficiently high, your black hole is also much larger. As you can see here, 1 billion solar mass object can have a size of Jupiter's orbit. Forget the size of the Earth or Moon or even the Sun. The size of this black hole is much, much, much larger than the Sun, and still it can be a black hole. So a common misconception in our mind that black holes are very tiny object is not actually true. We have discovered many supermassive black holes. The black holes with mass 100,000 solar mass, 400,000 solar mass, or even 1 billion, 1 million, or few tens or hundreds of million solar mass, and they are very gigantic in this size. So these are at one extreme where the mass of the body is very high. Let's go otherwise. Hypothetically, if I want to convert sun into a black hole, as per our current understanding, it is not possible. Sun cannot convert into a black hole because sun has not sufficient mass to produce that gravitation to shrink its own mass and convert into black hole. So that is not realistically possible. But hypothetically, if we assume that we convert sun into a black hole, then the size of the sun will be limited to only 3 kilometer radius sphere. Same way, if I want to, make a black hole out of Earth, then the size of the Earth will be barely 1 centimeter, size of a kind of a plain marble. And let us go even further extreme and assume that all human population on the Earth, I want to, convert into a black hole, then all human population will have to be size of comparable to proton. one of the smallest particle, size of the proton, to become a black hole. So you can assume, you can understand that how dense these black holes are. So there are two types of black holes, as I have already explained. Some of the black holes have mass few to few tenths of time of solar mass. Their mass is few to few tenths of time of a sun. And they are called stellar mass black hole because their mass is comparable to a star. They are called stellar mass black hole. There is other different class of black hole, and they are called supermassive black hole, and their masses are few 100,000 to few millions of mass of the sun. And this triplet, Professor Roger Penrose, a theoretician, a mathematician working in a theoretical physics, who contributed significantly in the theoretical development of a black hole, and other two fellows, Professor Genzel and Professor Gaze. Independently, these two scientists, along with their team, they have discovered a supermassive compact object in the center of our own galaxy. For their theoretical and observational experimental contribution, they were awarded Nobel Prize in 2020, just few years back. In COVID era, they got this Nobel Prize. So let us go through this journey. How do they discover a supermassive black hole in our galaxy? Now, apparently it seems appear because these black holes are supermassive, so their sizes are very large, and large size objects are easy to discover because these black holes are not luminous object. As I already explained, the black holes are dark object, and discovering an object which is not allowing any radiation come out of it is really challenging. So how do they discover the supermassive black hole? So not only these two scientists, but many other generation of scientists, including these three great giants, have contributed significantly. Two of them I have already introduced, Professor Einstein and Professor Schwarzschild. One more scientist I would like to remember here, and he is Professor Subramaniam Chandrasekhar. Professor Subramaniam Chandrasekhar has also worked significantly on compact objects, including white dwarf, neutron star, and specifically on black hole, and given a very good theoretical framework to work on the black hole theory. Continuing our journey to discover this black hole, you know, what you are looking is a famous picture. All of you can recognize this is a galaxy. Now you all know, I'll take some time and introduce this galaxy. This galaxy is a galaxy very similar to our own galaxy, Milky Way galaxy, which the sun and the solar system resides. Remember, this is the real photograph of a galaxy, small galaxy, but this is not the photograph of our own galaxy. We cannot take such a nice, beautiful picture of our own galaxy as we are residing inside. Being in our own galaxy, we can take pictures of other remote galaxies. But it is not that easy, very challenging to take picture of our own galaxy. It's like, you know, living in a house and taking picture of that house, how it appears from the outside. It is not possible. But as I told, our own Milky Way galaxy resembles in shape and many other aspects in this galaxy. So you can see this galaxy has a very bright and dense core, and there are spiral shaped arms coming out of this galaxy. The arms are spiral in shape, but not very sharp and precise. They are little fuzzy structures. Some of the bright stars you can see, in this arms, but most of the stars cannot be seen, individually. So primarily this galaxy is made up of stars, gas, and dust. So not only stars, but the space between the stars is filled with various type of gas, primarily hydrogen and helium, and a percent or even less times heavy elements. And also it comprises of dust, which is 1% of the total gas in the galaxy. So amount of dust is barely 1% of the total material in the galaxy, and still dust, is one of the dominant parameter control the dynamics and structure and evolution of the galaxy. There are 100 billion to 200 billion stars in this galaxy. This galaxy is made up of 10 to the power 11 to 2 into 10 to the power 11 stars. If you cannot appreciate this number this way, then let me tell you this way, that take a single pixel of this image, single pixel, and that pixel itself may contain maybe 1,000 to 10,000 of a star. So it's, that gives us an idea that the size of the galaxy is also quite large. So I can tell you this way, that, let light travel from one end of the galaxy to other end of the galaxy. Let us assume that a light ray traveling diametrically opposite to points. So it takes almost 100,000 years for a light to travel from one point to other point. So the size of a typical galaxy is 100,000 light year. So it's a huge, large structure comprising a real large number of the stars. Having this large size, even this large number of the stars are quite separated apart from each other. Like in our case, Sun. The nearest star of the Sun, that is the Proxima Centauri, is almost 4.3 parsec away from us. And that shows that how feebly these stars are distributed, how sparsely the stars are distributed. So don't assume that this galaxy comprises 100 billion stars. So all stars, tightly, compactly arranged and structured, and they are colliding with each other very easily and occasionally and frequently. No, it's not like that. All the stars are distributed in very large. Each star maybe domaining its own region of 1 cubical light year. So stars are not tightly packed in this galaxy because galaxies are very large. Before moving ahead, I give you an idea that assume this large galaxy comprising this large number of stars is just a unit for our universe. Like a cell is a unit structure for a human body or any living body. Cell is a unique unit structure. Similarly, galaxy is a unit structure when you are started describing whole universe and its structure. So for one galaxy, the other galaxy is a point-like structure, point-like object, because separation between two galaxies is actually million to billion light years. Millions to tens of millions to hundreds of million light years away from each other. So they are actually, very sparse structure. Our universe is real huge and sparsely distributed. Most of the space is, filled with a very feeble amount of gas and dust. Otherwise, it's empty. This gives you an idea how large our universe is. Our sun, let us assume this is a Milky Way galaxy. It is not actually a picture of Milky Way galaxy, I have already explained, but assume it's Milky Way galaxy. Our sun is lying somewhere here, 3/5 from the center, 3/5 of the radius from the center. The sun is lying somewhere here. And if you want to see the sun and the solar system, then you have to use electron microscope for this image. And the smallest particle you can see using electron microscope will be maybe a solar system. So, solar system is really insignificant in terms of galaxy or in terms of universe. And forget solar system, we are residing on just one small planet of that solar system. And we have no idea where we are actually living. The galaxy is actually a two-dimensional kind of a structure. It is not actually three-dimensional spherical structure. If you see it on top view, you see this spiral shape. But if you see it from the side view, it appears as if a disk of gas, dust, and stars, and there is a slight small bulge-like structure in the center. So it is more or less a two-dimensional structure. कई बार हिंदी में हम सीखते हैं ना, गैलेक्सी का स्ट्रक्चर पूरी जैसा है, जो खाने की पूरी होती है वैसा है. It's two-dimensional with slight elongation in the third axis, third dimension. What we are going to talk about is what is there in the center of this galaxy. Center of our own galaxy. I have just explained you we cannot take a picture of our own galaxy. But here, it is our humble effort to take a picture of our own galaxy. What you are seeing is a real, actual picture of our own galaxy. But you may ask that how is it possible? We are residing in this galaxy. How can we picture our own galaxy? The reason is this is, I would say, a panoramic view of our galaxy. We take picture of the many pictures of the small parts of the galaxy, cover whole 360 degree, and then match them. We merge them, and then we produce this panoramic picture. So what you are seeing here is actually a panoramic view of our own galaxy. You can see it is also a two-dimensional structure, disk-like structure with a central bulge, small central bulge. How many galaxies are there? You can see this is also a real picture taken by Hubble Space Telescope. This is the picture of a deep, deep space where you can see, if not thousands of, you can at least see hundreds of different galaxies in different shape, different structure, different orientation. And not only that, if you carefully see, some of the galaxies are interacting with each other. They are, I would say, colliding with each other. So, universe is full of galaxies. As I already said, a single galaxy comprises 100 billion stars. Similarly, our universe comprises of 100 billion galaxies, roughly. Nobody has, counted all these galaxies. This is our rough estimation. And the estimation says that number of galaxies are again 100 billion to 200 billions in our galaxy, in our universe. Some of the galaxies we started observing from 1960s appear to be very bright, and their center appear to be very bright. Like here you are seeing is actually a radio picture of a galaxy, which is called M87 galaxy. So this galaxy, if you see this galaxy through radio waves, in India we have many radio telescopes available. One of the largest telescopes is called GMRT telescope near Pune. It is called Giant Meter Wave Radio Telescope, GMRT. At some point of time, it holds the world record of largest telescope at 1 meter wavelength. Now, anyway, many more, much larger facilities come up. So, one of such radio telescopes is observed this galaxy M87. This is called active galaxy. Why it is called active galaxy? Because if you see the center of that galaxy, you will see huge amount of light coming from the center of the galaxy. And not only light, sometimes you will see a large jet of gas, spike of gas coming out of that center. They are actually called jet. Again, remember, the size of the jet may be billion times larger than our own solar system. Because solar system may be much smaller than a single pixel in this picture. So you can assume how large this jet of gas and dust is made. So we have started discovering such active galaxies whose center is very active. And these active galaxies are not always nearby galaxies. Some of them are real far galaxy. They are called quasars. They are called quasar or quasi-stellar objects. They are so far from us that we cannot see at all. We should not see at all. But they are equally bright. They are very bright. And so we can see them. So when these quasars were discovered for the first time, it was a real puzzle, real challenge for astronomers, that what kind of physical mechanism is going on there who produces this huge amount of light. Excuse me. The estimated amount of light, you can imagine, the estimated amount of light emitted from these quasars are billion, 3 billion into billion times brighter than our own sun. So you can assume how bright these objects are. You may start wondering now, in astronomy, all the numbers, all the quantities are really astronomical, whether it is time, whether it is dimensions, whether it is temperature, whether it is pressure or brightness, whatever. So in astronomy, everything is astronomical. All are large. And that's real fun playing with all these objects. So the question comes, how do we get this huge amount of light from these active galaxies? For decades, this problem was unresolved. And finally, now we know a real possible answer of this object. And the answer is that all these active galaxies comprises a supermassive black hole in its center. This black hole eats material from the surrounding. But before eating that material, it allows it material to spiral around itself and allow them to form a disk. And before, swallowed by the black hole, this material, the gas and dust and maybe whole star, get heated up to millions of degrees Celsius, millions of Kelvin. That's very huge temperature the material gets heated up before swallowed by the black hole. From where this heat comes? Primarily from the conversion of gravitational potential energy into heat energy through viral theorem. Nowadays, everything appears as a viral after COVID. So how do we know the existence of these black holes? So we have studied the material close to the center of this galaxy. And we see that the light coming out of this material indicates that the material here are moving away from each other. If one region is moving away from you, then the other region is coming towards you. That means black hole is allowing the stars and gas and dust to revolve around itself. And if you discover the revolution, if you have some estimation of the mass, then you can estimate the mass of the central object also. So by spectroscopic techniques, we have discovered red shift and blue shift in these regions, and that gives us an indication that these regions are moving very fast, revolving very fast around the center. And this gives us a clue that the center is actually made up of very heavy, massive, dense, and yet small object. And that can be nothing but supermassive black hole. But all these stories are about other galaxies. The question comes, we have just seen that there are so many galaxies, even in the close vicinity of our own galaxy. The question comes, how many of these galaxies comprises supermassive black hole in its center? This is an interesting study. So, in 1980s, two groups independently started working on it. They have selected a sample of different type of galaxies and started studying this galaxy for supermassive black hole in their center. And they wanted to estimate how many percentage of the total sample comprises this black hole. The answer, is very surprising. At the end of the study, they realized that almost all these galaxies comprises supermassive black hole in their center. Almost all these galaxies. Some of the black holes are active, emitting huge amount of light by eating material. Some of the black holes are not that active. They are not swallowing material around it, but they are there. They are revolving stars and gases around it in orbit. So the first result comes from this study is almost all galaxies comprises central supermassive black hole. The question comes, how do this supermassive, huge, massive black hole forms in center of each galaxy? The answer is we don't know yet. This is still an open question. We don't know how these supermassive black holes form. There are several theories proposed, but no theory has an observational evidence. Moving ahead, if all galaxies comprises supermassive black hole, then what about our own galaxy? We are living in a galaxy called Milky Way galaxy. It has a very nice, extended, bulgy center. Do our own galaxy has a black hole, supermassive black hole in it? We had no direct evidence for this supermassive black hole in our own Milky Way galaxy. The problem comes here. Why do not we have an idea? The reason is, when we start picturing the center of our galaxy, what you see here, this blue, orange and red kind of a fuzzy image is actually a real image of region close to the center of our own galaxy. The center of this square, very much here, is the center of our own galaxy. It's the center. So when you picture the center of the galaxy, you will see very fuzzy, unresolved stars and objects. When you cannot resolve these stars very nicely, how do we study their motion? And if you don't study their motion, then how can you prove that all this motion actually done by powered by a central supermassive black hole? So this kind of fuzzy, dull image will not help. But the problem is, when you look in the center of the galaxy, this bulgy region, as I've already said, made up of gas and dust. And this gas and dust absorbs huge amount of optical light. So very feeble amount of light will reach you and you will have very poor quality picture. One of the solution is that you start observing them in higher wavelengths, longer wavelengths, like radio waves or like infrared radiation. Radio waves will not help because most of the stars, ordinary stars, are not bright in radio waves. So what remains is infrared radiation. So what you see here is infrared radiation, and because of infrared radiation only you can see these stars. But the stars are very fuzzy. Reason is our own atmosphere. A thin layer of atmospheres, around our own Earth causes the picture to blur significantly. In this animation, you can see it. Let us assume the light coming from the central source. When it is coming and when it passes through our atmosphere, the nice sharp wavefront, when they enters into the atmosphere, they starts getting blurry. And when you observe this light, blurry light through a telescope, you will see the picture is quite blurry and moving. You can see here. See, the star picture is moving and makes eventually blurry. So our own atmosphere actually distorts the wavefront and makes the picture very blurry. Now we cannot remove atmosphere to get good picture. Neither we can send these large telescopes in the space. The largest telescope we have sent in the space is James Webb Telescope, recently launched. And that is also a recent project, a very old project completed recently. But earlier, all the large telescopes, even much larger than James Webb Telescope itself, are ground-based telescope. And for that, atmosphere is always a limit. You cannot get good picture because of the atmosphere. How do we resolve this problem? So scientists and technologists, scientists and engineers, hold their hands and come up with a very nice solution. I'm trying to explain you here. This is a star which emits a light. That light has a distorted wavefront. The wavefront is distorted. When this wavefront reflects on a mirror, so there is a thin mirror. It's like a plastic mirror, very thin plastic, micron size plastic mirror. So this light gets reflected by plastic mirror. That mirror will split light into two parts. The image of the star gets splitted by two parts. One part will go into your CCD, which takes the image of the star. The other part goes to what we call wavefront camera. So what this camera does is, it tries to measure the distortion in the wavefront. The distortion in the wavefront. The distortion in the wavefront actually calculated by this control system. It will give command to this deformable mirror. This mirror, as I've said, is a very thin micron size plastic mirror, and this mirror can be deformed into the shapes, desired way. We can deform it. So our control system is deform this thin mirror in such a way that the deformation will actually make this distorted mirror a plane wave. So deformation in the wavefront get cancelled by totally opposite side deformation, conjugate deformation of the mirror. So wavefront deformation, mirror deformation will cancel each other, and finally you will get very plain wavefront. And there you can get a very sharp image. This is called adaptive optics. This loop that a light get reflected, wavefront get detected, calculated, and mirror get deformed. This closed loop, is very fast loop that goes to few kilohertz rate. Every second, few thousands of times, this wavefront get detected, measured, and corrected. So this adaptive optics is one of the sophisticated technique we have discovered. And see how the effect of this technique comes. When this closed loop starts, your blurry star become very sharp here. So this system make your star very sharp. This is anyway animation. But if you see the blurry image earlier you get through the telescope without adaptive optics, become very sharp image now. You can see each and every star in this image. Both these upper and lower image are real image. Without adaptive optics, you cannot see many stars in sharp structure, but after adaptive optics, you can see many stars very clearly. Now, thanks to this adaptive optics technique, you can picture the stars in very sharp manner. I'll skip this, but yeah, the simple technique I have explained in couple of minutes, the adaptive optics technique, is not that simple and that easy. The actual system, what we call adaptive optics system, are very complex systems, and you can see how complex they are. Because just taking picture at few kilohertz rate is not possible for our ordinary camera. Here you are not taking pictures at few kilohertz rate, you are analyzing them and you are deforming your mirror equivalently. So this is very sophisticated technique, and that helps astronomy a lot. Using this technique, two groups of scientists led by Professor Andrea Ghez, and Professor Renard Genzel. Andrea Gez's group was working in USA, whereas Professor Genzel's group were working in Germany. So both this group independently used this adaptive optics technique to picture the center of our galaxy. And what you are seeing here is the real picture of the center of our own galaxy. Now you will see that the stars are again very blurry. I have just said that after this adaptive optic system, we can see stars very sharp. How do they appear blurry again? The reason being, what we see here is just a small central portion of the star. Let me, yes. It's a very small central portion around the center of our galaxy. If you see a larger picture, you see stars quite sharp. But when you see a very small field of view, again the star appears as a bulgy structure, but they appears very clearly. So you can see that the stars are very clear here. They have not only taken the picture of the center of the galaxy, they have taken the series of pictures at different times. Every year they took few pictures. So now you have a series of pictures. It is called time series of the pictures. And when you have a time series of the picture, you club them, you merge them, and you can make a video. And the video will show the motion of the stars. So what you are going to see is the video of the motion of the stars very close to the center of our galaxy. Yeah. And you can see the stars are clearly moving here. Here I am showing the motion of the stars. It is a slow motion. I'm running it again for better clarity. I hope you can see this videos also clearly. So apparently these stars appear to be moved, but not in a systematic way. But when you track one single star and move their motion, you can see that they are actually moving. They are moving around a common center. Some of the stars, So some of the stars are, moving in a very large arc, whereas some of the stars are moving in a very, very elliptical, narrow elliptical orbit. Some of the stars in very nice elliptical orbit. So all these stars are moving around some common center. And what is their common center? The common center is here. If you can see a symbol of star here, you can see that common center is here. This is the image produced by Professor Gay's group. And here what you are going to see. This is the simulated motion of real observations. You can see here from the cake group, that is this Gay's group. So you can see all the stars, they have different name also, right? All the stars has S08, S017, S061. So they have identified hundreds of stars around the center of the galaxy, and some of the stars they have tracked here. And you can say that S16, S8, maybe S19, they are passing through close to the center of the central object. Motion of all these stars is a good indication of a very dense source here. But how dense, how big it is, how massive it is, if we know these two numbers, the mass of the source and the size of the source, we can calculate the density of the source. And that has been done by both these groups. You can see here it is the three-dimensional simulation. Forget all the stars and their orbits. If you only see one star, you can see that it is in an elliptical orbit. When it is at apogee, the farthest point, it is very slow. But when it comes down close to the central source, the central source is appeared as a bright source here. It's not bright source, yes. So that is very fast. And the motion is 0.2 2%. If you see 2% of the light, let me show you again. Yes. So if you see the motion of this star is almost 2.5% of the speed of light. That is how many? If you can count, 27 million kilometer per hour, or it is 60,000 kilometer per second. So a single star is moving at 60,000 or maybe 70, 75,000 kilometer per second. So it's a very fast motion. What happened? That actually, when we see this kind of a motion, we can estimate the mass of these individual stars from some other technique, what we call the HR diagram technique, the color magnitude relationship. So if we measure the temperature of the star and if we measure the luminosity of the star, that can be measured directly through observations. If we measure them, then we can estimate the mass of this individual star. Using the mass of individual star, using simple Keplerian equation, all three laws given by Kepler and Newton's gravitational formula, you can estimate the mass of this central object. So you can estimate the mass of the central object using this method. How will you estimate the size of the central object? So what they have calculated is, if the central object is somewhere in the center here, this star, this particular star, reaches this close to the central object and then safely come out. That means the closest approach, the central object is even smaller than the closest approach. If the central object is larger than the closest approach, then they will have a collision here at the perigee, and there this star cannot survive and come out. So there is no collision here. That means the central source has size smaller than the central approach of the star. Central approach has been calculated already from the Keplerian mechanics. So all this mathematics is apparently easy, but when you try to apply it, it's quite sophisticated. From these calculations, what we got the numbers are, the central source is actually 400,000 times heavier than the sun. But at the same time, its size is smaller than Jupiter's orbit. If you calculate the gravitation of this object at its surface, you will see that the escape velocity is more than speed of light, and that means a few 100,000 times massive star within few astronomical unit radius can be only black hole. There is no other possibility. So with this technique, both this group have, after doing this study for 2 decades, they were studying these images and these centers for 2 decades. After this 15-20 years effort, they have proven that yes, there is a central black hole in the center of our own galaxy. And this way, we have proved the, what is happening? Oh, sorry. My presentation got in. Are you able to hear me?
Yes, sir.
Am I audible?
Yes, sir.
Sorry. Yeah, am I audible?
Yes, sir.
Okay. I prepared myself, so I could not hear your answer. So yeah, with this journey, I have just given you a flavor of how a black hole can be and how have we discovered in the center of our own galaxy. So now we know for sure that there is a supermassive black hole in the center of our own galaxy. And then recently, just last year or so, we have actually, I would say, imaged the central black hole also using very sophisticated technique and radio observations. So yeah, I hope now you have some flavor of what kind of a black hole is there in our galaxy. Thank you very much. If time permits, we can take a few questions if some of you have.
Okay, thank you, Dr. Vishal Joshi.
Thank you.
Thank you, Dr. Vishal Joshi.
Thank you, sir.
Okay, now from the audience and from the participants, if they have any question, we invite participants for any questions. It was an excellent talk on the
Thank you, sir.
presence of supermassive black hole.
Yeah, I can read a question in the message. The question by Mr. Nayan Mani Das. So how is it possible for an instrument to take picture of an object which is millions of light years away, as the light coming from such a large distance will take longer time? Is it so that the image we are seeing is today's time is a picture of some old era? Kindly illustrate. Yeah, I completely agree with you, Dr. Das. So what we see is actually not the farthest object. We are also see in the past. Actually, there is nothing like, I would say, present in physics. Present means simultaneity. You are there, I am here. I cannot say that now you are hearing me, because you will hear me few seconds after I complete my speech, because it takes light or sound to travel to you. So if you study the special theory of relativity, Einstein has clearly mentioned the concept of simultaneity is very difficult to hold in space. So farther we see, deeper in the past we see actually. So that's very true. And that's why this James Webb telescope is designed to see the farthest object, so that it can not only see the farthest object, but also it can see the deepest object developed in the deep past. And they actually see the early stars and early galaxies from some billions of years. I'm getting some noise. Yeah. So yes, if our telescope see a very bright object millions of light years far, we are actually see this object how it appears millions of years back. I can read one more question from Sandeep Rai. Sir, if our galaxy have a black hole in the center of our galaxy, then how is it possible that the bright light we can see in the center of the galaxy, and if black hole, there should be a dark spot in the center? Yeah, it's again a nice question I used to get from the audience. The question is, if there is a black hole in the center of the galaxy, it should appear dark, black, but we can actually see it. The reason being, as I already said, all these black holes, swallows material around it. Some of the black holes, eats at very high rate, and they are called active black hole, and the galaxy it hosts are called active galaxies. But black holes and supermassive black hole, like in our own galaxy, are not swallowing material at very high rate, but still it, allow gas and dust to circulate around it. The circulating material are very hot. As I said, few millions of Kelvin temperature they holds. The circulating hot material emits light, and this light we see. So what light we see are not coming from the black hole, but it is coming outside the black hole horizon from the circulating material. So black hole appears dark, but materials circulating around the black hole are very bright, very hot, and we can see that material. Thank you. Can I take some more questions, sir? Let me take one more question. It's
Yeah, you can take.
Thank you, sir. So it is Mr. Aman Rathod. Is there an interference between a photon of stars from stars to our telescope? If yes, then how can we say that we get light from only one particular star? Yeah, so what I understand is if we are observing a single star, there may be many stars in the line of sight. How can we resolve them? So yes, if we see in a particular field of view, there are many stars are there. Some of the stars apparently close by. They are not actually close by, but they appear to be very close by, and their light may get merged. But many of the stars are isolated. As I have said, all the stars are sparsely distributed in the galaxy. So if you take a very small field of view, then you can see individual stars very clearly. And we have studied these individual stars. Still, we cannot say for sure the light coming from a specific star is its own light. It may be light contaminated by some foreground or background star also. So for that, we need to study the distances also. If the distance also maintains, then we can say, yeah, that the light is coming from this distance and there is a star at this distance, so we can match it. Some more questions I'm receiving. How a black hole engulfed by other black hole will be identified? Yeah, so it is right like merging two black holes. So not only black holes, engulf just other stars or gas. Two black holes can, fuse, can collide with each other and fuse into single black hole. And this kind of black hole collisions primarily nowadays detected by gravitational waves. So now we have capability to detect gravitational waves, emitted from two merging black holes. I have a separate presentation on it, but time will not allow. So yes, the gravitational wave helps us discovering two colliding black holes. Some more. Can you please explain the theory of relativity in terms of galaxy? That's a real challenging task for me to explain the theory of relativity. It's a large subject. I invite you to study in detail using some standard textbook. Thank you. How black hole can is it possible the galaxy here? Yeah. The question is it possible that other galaxy have solar system and life? Again, an interesting question. Forget other galaxy. Even in our own galaxy, there are 100 billion stars. One of the stars is Sun, having this solar system, planets, and one of the planet hosts life. We have, since last 30 years, we have started discovering planets around other stars in our galaxy, actually in our neighborhood part of the galaxy. So now we have discovered almost 5,000 different planets revolving around different stars. And not one planet revolving around one star. We have discovered many stellar systems also, that 5, 6, or 7 planets revolving around single star. Some of the planets may hold life, may hold. So as a scientist, as an astrophysicist, I don't deny that there is no life in the universe except on the Earth. At the same time, I also say that we have no direct or indirect evidence of life apart from the Earth. So we are searching for that. Many scientific programs, observational astronomical programs, are going on to search for life signal in the distant stars solar system. But it's very challenging and very difficult. It's very slight hope that in near future, in few decades, we will be able to search for any other life. Also, when we say life on the other system, most of the time, the concept of alien is there in our mind. but not necessarily the life in other planets is well evolved, intelligent, and outsmart also. They may be very tiny single molecular or single cell structures also may be there. So life can be of any form. So yeah, there are possibilities, but there is no confirmation.
Okay, fine. So I think if there are no questions, Vishal, I have one simple curiosity. There is one word I read, Sagittarius, in
Yes.
this subject. Is it related to constellation of zodiac?
Yeah, so it is the same Sagittarius zodiac or constellation we assign with ourselves is the same. So basically, all these zodiac are actually part of the skies. So we have divided one specific circle of the sky into 12 part. This and this each part is actually associated with one zodiac, the stars in that. So yes, so Sagittarius is a zodiac for us, but it is actually part of sky for astronomers and center of the galaxy. Yeah. Thank you.
Okay, thank you very much for giving this nice talk. Very interesting and beautiful talk. Thank you very much, Vishal Joshi. Thank you very much.
Thank you.
Now, I would like to invite our next speaker, Professor Dr. V. Ganesan, sir. Let me give a brief introduction of Dr. V. Ganesan. He is a so eminent scientist in India that he doesn't require any introduction to the material physicist. But just I have to give some introduction before his talk, so let me give in a very brief, because it is not possible to give complete introduction. He is very eminent scientist of India. Dr. V. Ganesan is at present Dean of Research Affairs in Medicap University, Indore, and is former Center Director of UGC DAE Consortium for Scientific Research, Indore. He has 40 years of research experience, and he is known for setting up sophisticated laboratories, low temperature and cryogenics and SPM labs. He has initiated large number of CRS projects at RAJKOT, synchrotrons, and more than 200 CRS projects countrywide. He has many research publications in reputed journals, more than 500 publications and 10,000 citations, and H index is about more than 50. He is a recipient of CSR Scientific Excellence Award 2010, and he has been a liaison officer of UGC DA CSR Kalpakam node for 6 years. And he has supervised more than 17 PhD students and handled many research projects involved in 3 DST and 2 UGC projects. And he has also visited foreign countries, the Berlin, Germany, and under DST, DAAD project twice to bring a dilution fridge as a gift to CSR, and a visit to MPI, Germany, to learn about turbine machines. So we are extremely fortunate that he has agreed to spare his valuable time to deliver a talk in this event. And let me tell you, the audience, that it is a real pleasure of learning physics from Dr. Ganesan. I humbly request Dr. Ganesan, sir, to deliver his talk on scanning probe microscope. Dr. Ganesan, sir, please.
Very good afternoon, Professor Joshi. Am I audible?
Yes, yes.
Yes. I'm very thankful for your nice introduction. And it's my pleasure to be with you virtually at Saurashtra University, which I already visited many times, and many of our friends also there. I also would like to thank Professor Shah as well as Piyush Solanki and all the organizers of this very beautiful conference series virtually. And then I think someone can help me that I can share my screen. Someone can. It's not getting shared. I think someone should permit me. But the option is not coming. It says you are not allowed. Sir? Yeah, that's what I am clicking. It says that you are not allowed to share. So what I should do? Something very. Okay. No, same what I am talking in my laptop only. Where my PPT is there. 1 minute. Can you? I want to share my screen. Do you know any problem? You are not allowed, it says.
You're not allowed to what?
No, I want to share my screen, talk.
Okay.
This is the one, na?
This is.
Present now.
Yes.
इसी में कुछ हो रहा था.
Sure. Want to share?
No, my talk is here, PPT. Just come to choose the file.
This one.
Maybe there.
Yes.
Okay. Sir, is it visible now? Hello? Yeah, thank you very much. Okay. See, most of my this scanning probe microscope for the last 20 years, apart from me, 2 students have done extensive work on this, including for the users are Manju Mishra Patitar and Dept. So let me talk, give due acknowledgement to them. I would like to thank the entire Vigyan Yatra 2024 for this nice invitation. Professor Joshi, Professor Nikesha, Professor Piyush Solanki, I think for the invitation. I would like to thank our Medicaps University for the support and UGC DSSR where earlier I was there. They helped me a lot. And of course, we have some good amount of funding from UGC, DSSR. That's why we could able to do some good work. And Dr. Nanda and Dr. Chipnis from Chaitram Hospital Research Center did some work with me for the very nice biological system. So it was very useful. And then Dr. Neetu Badera and Dr. Richa Panda did quite a good work. And Dr. Venkatesh is now heading my lab. So it's very nice extending the facilities. And Mr. Mohan was my technician. Pras Srinivasan is my mentor. So I have to tell him that he will introduce me to this beautiful system. So the frontiers of microscopy is so nice. The first Nobel Prize for X-rays, and then everyone was aware of the X-ray diffraction, and all the way up to wax and Crick DNA, fiber diffraction. In all of them, we try to see a reciprocal lattice. Can I hear? Am I audible, sir? I have done already a full screen only. Okay. That's what I did.
Hello, sir. Hello.
That's what I'm asking you. Is it okay now? Is it okay? Oh, I'm not sure, but it is full screen here. If somebody can help me. 1 minute only, sorry for. See, they don't see the full screen. They see only this screen. So I shared it fully here, full screen.
You need full screen.
Hmm.
You need full screen?
Full screen is here, no?
Yes. You need or not?
They want. That's what I was trying.
So, sir, after pressing this sharing button, there are 3 tabs. So you have to click on the 3rd tab, that is entire screen, and then select the window.
कुछ काम कर रहा है?
Nothing is working.
Wait a minute. Why?
I think it will refresh. Then you can refresh it.
Huh?
अपना पेज हाँ ठीक है.
1 minute, sir.
Just stop sharing and share again.
Wait a minute.
Nothing is working. Yeah.
Stop कर दिया. है ना?
Yeah.
Now how to do next one? Unless you cannot see other window.
Just
Go like this.
and show.
PowerPoint and
Sir, 1 second.
already
They are seeing like this, but not doing. Now entire screen हो जाएगा. Am I now? It's full screen now here. Sir? Hello?
No, it is not full screen.
Oh.
At your
But I
place,
think this
it
is
is
fine.
fine, but at this end, it is not.
Okay. They are not seeing this. They see this. Okay? Which one? Thanks, sir. Yes, sir. There's a Chrome tab window. Hello? There are 3 options are there: Chrome, Windows, entire screen. Yeah. Oh, okay. Oh, okay.
No, even after clicking on entire screen, they have to click on the screen before sharing. Then only it will be implemented.
Is it okay? Okay. Thank you.
Okay, this is fine.
Okay, thank you. Okay. I was mentioning that so far, for the first 80 years of the last century, we used to do most of our work on reciprocal spaces, and we used to get so-called Lagrange spots or SQL indices, and then try to make a model that suits the intensities. Then we try to make a computer program to fit your model structure to that. We never visualize submicron structures except in electron microscope. So there is always a demand for seeing structures in a real space representation. Scanning probe microscopy has become a very nice tool for us to study this. Let me go on a student viewpoint how to learn about scanning probe microscopy and their capabilities. The small picture in the left-hand top corner is what the first image that I did it for at TIFR. They are having the first countries almost first working very nice scanning probe microscope, and ours is roughly second or third in the country. So it is about 1994 somewhere else. So this is a very interesting form of submicron structures, so-called epitaxial high tissue superconducting thin films. And there was essential need for us to understand this at that time. So we were able to do very interesting structures and later on for irradiation. And then the second part is that we have tried to see that what happened to the damages when you work with inter-university accelerator center, those days called nuclear cell center. We used to irradiate it to produce flux in the superconductors. But not only flux killing, it also erodes the entire thing around the ground boundaries. So you can able to see how very beautiful like a banana tree structures are there. The entire grain boundaries are eroded, and conduction mechanism for this called swift ion irradiation. We used to work out models and a lot of work we have done with Dr. Kandilal and his group those days. And this is the atomic structure of a very nice mica and graphite. Both will look very interesting for a two-dimensional structures. And then we have this very interesting hexagonal network of Staphylococcus, a bacteria which you touch your faces, the pimples, you will get this bacteria. They are also self-albumin nanostructures, very interestingly, but in the micron, submicron sizes. Then we try to see how the conducting current space is called conducting AFM. To study the biological structures, we need to go something called tapping mode. I will come into the system. But you can see the current mapping of your photoconductors. And these domains, very beautiful fractal domains, are by the magnetic domains called. We can visualize the magnetism a little bit, very interestingly called technical magnetism. And then we went for a butterfly wings, how beautiful photonic crystals they are. And the left side is AFM and right side is called lateral force, which measures the friction map. I will explain you. The power of this in various dimensions, all the way like about 10 micron to 1 micron to 100 nanometer to 10 nanometer. This kind of logarithmically 4 or 5 orders of magnitude down the scale. I won't say nanotechnology, but at least you can enjoy seeing this structures. And then this is about 30 nanometer small, what you call site-specific drug delivery, where iron oxide particles are useful to carry the rifampicin particle. The entire thing is around 30 micron. Rifampicin molecule is outside, and inside you have to go and scratch and see there's a small nanoparticle of around 25 nanometers are sitting inside. This is very interesting. So this is done with the Professor S.P. Goraskar from Pune University. And then very final, my very beautiful image right side is something very interesting, looking like a galaxy. Just now previous talk, but then it is something very special for the tuberculosis bacteria, how it is being attacked by the D20 microphages in a microscopic world. So there's a logarithmically ordered images I showed you. And this is slightly a motivating lecture, so meant for the students. This microscope is so small, just of the order of your coffee flask, but very costly nowadays. It's about 2 crores. The bottom one is the one which I used. It was about 25 lakhs. It's called only one contact mode AFM, where you can see very good. At least hundreds of users have used and good publications came. So later on, this 1 crore machine at that time, now it's about more than 2 crores. Is given to us, so we could able to do a very good, wonderful other modes of the much more than that. Just more than seeing a lot of physical properties at nanoscale. Otherwise, it's not possible for you to study. You can't say a small nano rod, see how good conductivity. You can see a bunch of conductivity in bulk per measure, and you can assume it. But here you can see each one of the small things, how it works. So this physical property measurements are possible. So this is very interesting. It's not very important, and this is the image taken by the scanning tunneling microscopy. So the beauty of that is that it was the tunneling is a main concept for the scanning tunneling microscopy, and later on a similar one for the scanning probe microscope where both the system. But the problem is that what is important is that you need a very tip, microscopically sharpened tip. In fact, the end of the tip can be a order of few nanometers. This has to be positioned across the sample. Normally at the nanoscopic or microscopic samples are not very uniform, so you will have a roughness in that. So that's a big challenge to position it very nearer to the sample. So we need to, and also scan X, Y, Z. So normally as piezoelectric devices are very important, and then you can apply electric field and control result motion. And XY is meant for exactly like a sawtooth voltage and that of a ramp. What you do in a TV scan, how you do a TV scanning, same thing it is XY scan. So we have to wait for the developments of the piezoelectric devices, and then very beautiful analog to digital and digital to analog converters. That is why, even though tunneling phenomena from 1930 is known that, but then it was a long time. till 1982. Pinnick and Rogers did some wonderful experiment on silicon and then 7x7 reconstruction, etc. So the very interesting. Out of all these things, very important one is also a vibration isolation. Even what we speak and what you are hearing is of sub-micron size vibration noise. So you need to equip your whole entire room, not your table or something, noise free. If you do that, and some of them, if you do a conducting AFM with a laser light, etc., you need to be a dark room also. So then you can get a very beautiful signal. And of course, you need a patience to do it and tender hands to mount the tips, which are very expensive. I'll come. So tunneling is a very interesting, simple quantum mechanical phenomenon. Classically, there is no analog at all. If there are sample and the tip, assuming both sample and tips are metallic, okay? Because I'm talking about tunneling of electrons, so both should conduct. And now, if there is any barrier between them, it can be insulator, it can be vacuum, it can be simply say air or vacuum will be the very easiest insulator. You can position the tip, very sharp tip, and near the sample. And this is according to quantum mechanics. See, there's a wave function is very interesting. The progressive wave function will damp, and you will get a very small probability. The probability of finding a transmitted wave function, it is possible only by wave theory. Therefore, otherwise classically, it is not forbidden. Electron will get reflected as well. But in quantum mechanically, you can assume it's a wave function. It will also tunnel, and the probability of tunneling is 1 into 10 power 6 roughly. Therefore, it is very difficult for you. The currents are all of the order of, you have 1 ampere means you will get 1 microampere. So if you have 1 milliamp, 1 ampere is big current. 1 milliampere, if you are talking about current level, it is around 1 nanoampere. You should have a deduction system for that. Okay, and that is very important. There are a lot of other technologies I don't want to tell you. The current exponentially decay. That's very interesting as a barrier thickness. So it is very exponentially very sensitive also. So normally the tunneling current is exponential dependence. Okay, and then there must be a occupied density of states in the tip, but there must be an unoccupied density of states in sample. Therefore, there's a probability of tunnel. But anyway, but nevertheless, since it is exponential dependence, it's become very sensitive. Say from 1 Armstrong to 2 Armstrong to 3 Armstrong, if you move your tip, it will go by roughly exponential of that. So it will be a very fast decay. So its selectivity is very high. So that is why a simple sodium chloride 5 Armstrong distance, it is easier for you to deduct it when you go from sodium to chlorine to sodium to chlorine or whatever. Very interesting. This is one. And a little bit small complex, but it's not so complex, is the current. What you get will be a convolution of the density of states, rho t, sorry, suffix has gone. Rho t is density of states of the tip, and rho s is density of states of the sample. So dI by dB is very interestingly, if you do it, you will be able to, assuming the tip is a known material like platinum, normally platinum, sometimes use tungsten. It's very difficult sometimes to etch the tungsten, you need science solution. Platinum is good in gripping the platinum. You may get a viscous of the sizes of the 1 or 2 cell dimensions. Therefore, it's very powerful. And platinum is a very robust material with the known density of states. So unknown material can be discovered. So whenever we do that, I'm just showing some of the very famous STS plots. It is not only showing the atoms or anything, you can also see the properties of the material like a metallic or semiconducting or tunneling. In the cases of a semiconductor, at least you will see a sub-electron volt, like 1 eV or 0.7 eV or even 0.1 eV small. It's big number. But if you go to superconductors like MgP2, etc., or some of the conventional superconductors, the band gap is only a 2 milli electron volt, 20 Kelvin and below, or 10 Kelvin and below. So it will be around 1 milli electron volt, but it's very sensitive. And you will see the superconducting gaps in between them. And a lot of work has been done into the Josephson tunneling, single particle GI tunneling, and many other so-called point contact tunneling, etc. So very powerful tool, and it also tells you very good about the vortex matter in the superconductor. So now, the same group was worried within 3-4 years. If what you do with to see this nanoscopic for all materials are not metallic, so you need to have samples which are non-metallic or semiconductors or non-insulating. You can't get any current. What they did was very ingenious way. They took a small cantilever and put a small piece of a diamond. It's a micro diamond. Diamonds are very hardest material. They don't deform, and then they are very sharp. Okay, tetrahedral symmetry, and then you can see that even you can get a small micron size diamond particles which can be embedded over a tip lithographically. Okay, and then now diamond is very costlier. You are afford to waste those kind of diamond dust or whatever. So it has so much that silicon nitride is the next hardest material of the top AFM. Therefore, they use silicon nitride and grow lithographically over the tip. So in the absence of all electrical, magnetic, and any other interactions, you will still have a reverse interaction. That's what I showed you here. This simple low latency potential. They are attractive tight distances and they are repulsive at low. So low distances. So when you go nearer the sample, you have hardcore repulsion competition. Those tip actually repulse. This you can really visualize this repulsion, and you can make this as a feedback parameter. So and it is so nice that it is much more sensitive than the tunneling, because the distances something like the interactions are 1 by r power 6 and 1 by r power 12. No, this Lennard transpotential available aware of it. Therefore, even if you move by one Armstrong to two Armstrong, it is about a million times the force will come down. That is why they become very atomic sensitive. You can see when you move from one atom to another atom, the interaction, of course, it's not a single particle interaction, there might be particle to particle, but still it has a selectivity of the order of a sub-Armstrong levels. So this is very interesting. Depending upon which portion of this force comes, very nearer to the sample, of course, you must feel the hardcore repulsion. It's called non-contact or tapping mode for biological system, and I used to work on this so-called contact mode very near. It's called, or sometimes you can work here. It's much more easier for you to work in the near the contact mode. It may go and hit the sample, it may damage, but you can see the repulsive part of the attractive attraction. This portion is very interesting for us. This depends on the operator, and if you are operating with your hands, you can have the feel of them. Then you know a lot of things. And then these probes are very nowadays comes in the cantilever. The triangular symmetry is because in the rectangular cantilever you have a lot of noise comes out because of the inherent vibrations. Therefore, by the moment of inertia configuration, a triangular tip will be very useful for you with a stable configuration. In this triangle, the end with a small dot is shown here. Like if you go using a transmission electron microscope, you can see the diamond tip very nicely, beautiful. Then you can work on that very interestingly. This is what I was showing. This is a triangular tip. A small black dot, what you see here, is a real tip that gives you all the. Of course, now people uses even rectangular cantilevers because everywhere triangular will not useful. A lot of other mechanisms like magnetic force microscopy need to tap some resonances, and also I will come to you. The piezoelectric is very interesting. A tube piezos with inside and outside coatings. That means inside the tube and outside the tube, we have bias can be applied. So the it will expand in a transverse way. That means that if I apply along the radial direction, it will contract and expand. So it is useful for positioning the tip. XYZ is very complicated. They are written with geometry also. So one of the split piezos like X and Y. For the X to X prime, I mean one is inside the contact, is outside the contact of the tip. You apply a sawtooth voltage, and Y you can apply a ramp. This is exactly like our video of the TV. How you do that? Those who work on electronics know about it. Okay. So you can make the samples, all the three directions you can work on it. So this is one of the very neighboring institute of you. I think Dr. Deshpande must be there. I don't know. The tungsten selenide is a very beautiful. Now it comes out again a 2D crystal after 20, 30 years. It's a very beautiful superconductor if you intercalate with water. And these crystals are grown by the SP University of those days. They were looking for what to do with them. So one of the very interesting measurements we did it was at that time, we used to see them in our AFM. It's only a 5 micron AFM. You just see a small stripes you are seeing. It is not really stripes. They are, if you really see the cross section of them, it is like a staircase. Okay, and for a long time, they are called atomic terraces. And at room temperature, we are not working at a low temperature or anything else, but a very careful imaging. It's a small flake. The flake itself will be of the order of a 0.1, millimeter, very small, tiny crystal cloud by chemical vapor deposition in a laboratory source. But then you could see a very high level of this. People used to irradiate, see the defects and big pieces are gone. But I'm not talking. There's only one image I want to show how good the AFM is. And you see that this, if you see the steps of each of them, what is the vertical dimension of one step to another step in a Z direction, then you can see it is about 1.17 nanometer averagely. Okay, that's equal to 11.7 nanometer Armstrong. 11.7 Armstrong is the C lattice parameter of this particular tungsten. That's all. Now, You see, go and sit in one of these staircases and then go to much higher resolution. This is in 5 micron, this is in 5 nanometer. So go by 1,000 times precision. You will see a very beautiful hexagonal lattice of the tungsten diselenide. Here the distance between the two atoms are roughly around 3.7 Armstrong or 0.37 Armstrong. So this I understood. You see, this is AB axis and lattice parameter of them will be all 3.7 and 11.17. How it happen? Very interesting. A crystal will grow. To what it will go, you need a small disorder or a dislocation or a seed crystal. Something is needed for you, otherwise it will not grow further. So for that, you can see that they grow. The growth modes, there are many growth modes, out of which something called a screw dislocation is a very famous way of the crystal growth mechanism. See Kittel book. The end may you can study all this dislocation. What is a screw dislocation? If you move by one rotation, it will move by one pitch, one unit cell up. So this that is called Berger vector, and you can study some of the MSc students. It is there in the classes also. So you can see that one can see this is a big screw of few micron. I mean, tens of 20s microns. A small portion of that circle will look like a straight line. That is why these steps are looking like a beautiful straight line for you. So this has created enormous interest in 1996 and 2000, that area when this work was done. That also started believing that we can see very nice structures all the way up to nanometer scales, and a very good physics can be drawn. Of course, it takes its own time for you to understand what kind of growth modes in the thin films, etc. Small intensive. We have done a lot of work on different columnar growth and laminar growth and many other things. So I'm not going to do that this time, but we can really enjoy this physics. Now, this is just simple contact mode. I'm working on the repulsive part of the force curve. Okay. Now I can measure this force curve also. At large distance, not much interaction. When you come nearer from A to B, it jumps to the contact. It goes because attraction. Then once you go very nearer to that repulsive potential, it really repels. When you come back, it won't follow the same track, and it follows a stereotic path a little bit because the sample holds the tip for some time. Then you are up. That's why while approaching very far, it is straight. When you come forward, it goes jump to contact. Then after contact, the tip is hold. Therefore, the tip is holding, so cantilever will bend. So you have to pull actually. So because of addition, then suddenly it will release. So you see that all these processes can be captured by means of a called force curve. By seeing this force curve, okay, in a fraction of second you get nowadays because of very high conversion of analog to digital and digital to analog converters available thanks to that, but very costly. And pixels also very high nowadays. At least minimum of 1024 by 1024 pixels you can able to measure. See the how kind of digitization for a 1 microvolt can be done. Then you can see that large addition, large resources. It tells you always the area between the BH loop or PE loop or MH loop or Carnot cycle, whatever you say, PV diagram. All these resources will tell you how much is the loss, energy loss in that. So it is very interesting. You can see large addition of it, small addition only small explosive scope. Stiff sample, you don't see any explosives. Soft sample, you can't get, always getting attracted. And then if you have this deformation, plastic deformation, etc., along the attraction, all these curves, there are many such curves, I will not call force curve, will tell you a mechanical properties. How soft the sample, how hard the sample, what you can do with, is it a colloid, is it a diamond, or is it a graphene nanotube, or what it is mechanical properties can be very nicely studied. Ink cooling, if you apply a little bit more force, you can damage the sample and find out the stress, strain, and modulus of rise. I will come to that later on. Very interesting. It's called nano indentation. Will also consider. So this is a beautiful mechanical property tool for the nanoparticles. For a nano. Only problem is that these nanotubes or nanoparticles, etc., should be held in a substrate very rigidly to do all this work. I will also show you. It depends on the time available. So very beautiful island formation which I showed you here. Actually, this you go with the thin film unit, and the unit shows you something like about 15 nanometers thickness, etc. So, but then you can see that it is each top of the island is called columnar growth actually is about 500 Armstrong. So, and then in between nothing is there. So when you are at when you are coating a metallic film on a insulating substrate, they first start a small islands of metallic cluster. These islands will slowly grow, swelling, and finally they come and touch each other in percolation. So you see the initially non-metallic conduction and then followed by conduction. You can do it in a silver films very easily. One of our former directors was interesting to do this in our own laboratory where we are setting up a thin film unit and we did a for silver films. So these island formations are very good. You see a very big growth and surrounding is small growth. This is fractal dimension. You can study them. And banana trees like this. A big tree will be there. Surrounding small trees will come. Again, the small trees will come. This kind of growth is very interesting. It's the best example to do that. This is some of the indium antimony and gallium arsenide quantum blast from our CAD state. This was very interesting. He's one of the famous nonlinear person who has worked on that. And then, of course, it's a triangular, circular, downward, all the way our CAT, Manipur University, Kerala University. We have seen all over throughout the country. People have utilized it. They have very good friends, very good samples. They used to come all the way from Manipur to Kerala to Tamil Nadu to everywhere to use it because of the sanctity of this particular project, of the interest by the students who travel all the way to 3 days and come and do the experiment for a week or 10 days and go back and understand, make a physical model by the time you get a paper out of it. But very powerful. So this all like molybdenum oxide films, and you can see cadmium sulfide, very beautiful blisters. And then a lot of there is nothing else. Go to downlands, there are many. I will go on endlessly. Now, let me talk about one of the very interesting radiation effects that we did. This is about that we were forced to come into the AFM. We went to the AFR to make an SEM pictures of this thin film. It was highly demanded those days in ITC days. We don't have time, and whenever we try to do it, they say that your film is getting charged and we are not getting image, etc. So then there was a discussion with very interesting Professor Pinto, who was having the AFM. He said, this is one new microscope, nobody is interested to, why don't you do something? Then we learned there in 10 days. And then I did myself the experiment. He was kind enough to allow me to use it. And then we could see a very interesting, so Professor Ramchandra, IIT Madras, now he is there. He was there at that time in RAJKOT. So was postdoc, and we did a lot of experiment in the midnight when the time is free available. And it's a very beautiful off micron golden biscuits. We see ITC. The color is put to under because we are very fabulous to seeing this. And when you irradiate them, instead of getting a very good critical current, because every defect will act as a pinning center in superconductor. Those who work on superconductor know that. But then we could see a non-metallic conduction. We never understand it. And when we did AFM, you can see here every grain like this of a micron grain, if it actually goes, the surrounding is all preferentially sputtered out. Then we were thinking, what happened? See, then there are two models are called ion Coulomb explosion and a thermal ions spike models are there. In irradiation, those work, I think many of your groups are working on irradiation. So this YPCO is oxygen deficient perovskite. The grain boundaries are devoid of oxygen, therefore they become insulator compared to them. So insulators, they preserve the heat for a longer time. Therefore, amount of thermal spikes are very easy for them to understand. And they specifically erode. Therefore, you can see there is always a center surrounding portions are getting easily eroded by this. Same thing here is very clear. One grain to another grain. These are all the portion in between eroded. Now, what happened? This is a metal and this is a metal. The tunneling should happen. It's called NIN tunneling. And if the insulator is present in, okay, if it is still a superconducting, you will say SIS tunneling. So SIS tunneling will be a Josephson tunneling. SIN tunneling will be GRV tunneling. So accordingly, you can make resistively shunted junctions of the superconductor. We worked a lot in this. This is one of the first papers of my first student in 90s. But then later on, we did very good. You see that the blisters after radiation, how nicely on the silicon and tap silicon. It's a totally non-conducting specimen. Therefore, entire heat is absorbed. Short time it revolves. It's like lava coming out. And a lot of good models have been taken. This is from Professor Bharat's group. Incidentally, Rasnacharya will become a director later on. After Srinivasan and Bharat was a director, another director, some man like this. So this is very interesting. Simple plastic polyaniline. Okay. If you take a polymer and break all the bonds, what you get? You get it carbon and nitrogen and all the gases, whatever is there, they all will go away leftover is only carbon. Carbon at very high temperature and very high pressure normally has to turn to diamond. How do you know that? A very small amount of lateral force microscopy, you can see a very beautiful tetrahedral faceted small spots, which you are seeing right here. You can also see how hard it is. You can see the hardness also for a small polyamine, which is not at all hard, will become a hard inclusions. Then it's a beautiful small. It looks like a story, but they are the real stories, and it's very interesting. Then don't tell me that to convert me all the plastics into a diamond, but it's not possible. So, but then we interestingly did all these experiments over a period of time. And then, of course, this is done with Professor Shika Verma. She's a very known figure nowadays. She was there earlier in IOP Institute of UNESCO. I hope she's also still there. And then for them, we try to see a small amount of blisters formation about a low energy really. It's not a very high like 100 MeV and all. 1.5 MeV of antimony silicon. And we did a lot of very good work on this. What kind of directional dependence of the radiation can do with this. So it's a very powerful tool, metallurgical and material science and chemistry and physics. This is a very another interesting part. Unfortunately, I had only black images somehow. So this is something we can see very interesting. Everywhere there are blisters are coming out, very random. It is not one proportional to the number of ions that we see. It's our number 12 ions per centimeter. We don't have that much blisters, but there are some collective effects. It be some 4, 5, 1, I say. But it is a very huge effect of this, and every blister is surrounded by a small hole also. This has made us to make a very systematic study on that. You take a silicon, very nice crystalline peak, single crystal silicon. You started irradiating, the intensity will come down because you create amorphous fraction and totally you amorphize it. Now very small peak, nothing is there. Everything is get amorphized. You take such an amorphized silicon. Now you are so far introducing a very heavy ion like silver ions with about 100 MeV or 170 MeV. But then now change the direction. Instead of irradiating vertically to produce amorphous, after producing it out, change the direction to a Granson angle. Something like not exactly 0, but a little bit about 5 to 10 degrees. Then you can see that if the direction of this ion is coming, it takes the mud out and put like a gardener, how it digs a hole. It takes the mud and put it on the other side. So there is a dig here, there's a heap of mud will be there. Same way ion does it. Then we understand. That's what I'm putting the cross section. All the mud is here taken and put it into the spread it out over. So this will happen provided the ion can able to do one ion. Not is not one ion. There must be a collective excitations of the ions that can produce you a lateral momentum transport. Very famous. You can read this paper like this. And it all happens over by a very good scientific interaction between UAC and then GUJCOST University, and then our students and the Kandila students. It was a very nice interaction that we got. It's also some of the first experimental evidence, so-called should have ion irradiation in India at least, because up to that people thought that only nuclear collisions can produce all these damages. Electronic energy loss cannot produce; it will simply go like a bullet, etc. Then we now understand even at 100 MeV and 200 MeV silvers, you can able to see materials damage so much extent that you can explain textbook efforts like your Coulomb explosion or thermal spikes very nicely. So it's very interesting. That is why this electronically excited indium phosphate surface again gap. This will all see the kind of roughness you get it after radiation is very fantastic. Okay, and it was once upon a time is a peak of the science. People also do that, like vertically absorbing. These pearls are looking like defects, amorphous materials. Amorphous materials, large volume expansion. That's why. And then in the molten state, you change the direction. One molten island to another molten island, you can see there are lots of traveling. It's all random directions and random changes. So how you can able to get this rod formation using a accelerator, etc., are very fabulous those days. For Dr. Kosh is the IIT. JP Singh is one of our students, student. It's also very interesting. If you take the such nano rods and annealing at high temperatures, how they beautiful downlets are. They collapse and take to a small islands and then go into a very beautiful state and things. These all appeared into a very nice series of articles in Journal of Applied Physics and Applied Surface Science. That's why I'm able to get a good amount of papers also. And then we also studied locally IV characteristic, and also the fluorescent films, and also the multi layers like LBMO multi-layers. After the invention of manganites, I think our group is working on that. What kind of radiation before and after you do it? Then this is something very interesting story. Also, some students from Vigyan University, neighboring university, who don't have much funds and fellowships, but doing small work in their small laboratories, nanoparticles, etc. So, but a very difficult experiment. We spent a lot of time. Even a couple of tips were broken because these particles in a thin film is okay. They adhere to the surface. This nanoparticle, you put it in a glass slide or a mica space and etc. You have to be very careful. They don't stick at all. So when the particle, when the AFM tips moves on that, the particle will also start working it out. You will not get it. So the trial and error. Graphite is a good substrate, but it's very costlier. So we cannot get highly HOPG graphites, but we get some cheap quality of the local graphite ores and polish it, and then we can able to put the things into the system, and you can see this very beautiful nanoparticles AFM, and also find nano rods also. What is important is that these are, if you do it on some kind of a nickel bromide or nickel ferrites, etc., there are magnetism. So size dependent magnetism is the aim, but they are in a small university where not much are available. Then we did it something uh, reasonably. But you see that the chemical methods they produce such a uniform particles. They are exactly whatever size is about submicrons, about 100 or 50 nanometers. You can control the size. It is every particle look like same. That's very interesting. And then we try to do a small magnetization from them. From there, you can calculate what is the coercitivity and you can plot as a function of temperatures. And you already is ferrite particles. And then this changes. I have seen a grain. For some time it obeys. It's called carbon fittings. And it obeys, and after certain bulk, then it will start, it won't obey nanomagnetism anymore. So the size dependent magnetization can be studied. It was studied once upon a time. So that's for and then, of course, in Dockside, a lot of at least 1,000 researchers in India did on Dockside, even now people are doing it out. And on various conduction of aluminum doping, we used to measure resistivity. Then we try to see the evolution of the brain structures. We can correlate the resistivity because very important is our how to calculate mean-free path as well as localization for distance of the insulating transitions. It also undergoes a metal to transition kind of thing at but in Mega, we won't talk about metal to fluid transition. This is something like a localization to delocalization. I will, I'm not interested, but there's a very Anderson localization plays a very interesting. And then I think this is one of the organizers, Piyush Solanki's paper when he was a student. I think one of my friends, Dr. Kuberkar, was there earlier. I think he might have retired now. So it's a very interesting secondary grain code contribution to transport and transport, and very interesting for the nanostructured LPMO films. Using both TEM as an ACM as well as AFM. And while doing the AFM, we also try to do called LFM. LFM is lateral force microscope. Each of them, the top one is AFM and bottom one is LFM. You can see the clarity of the pictures. Okay, I will explain what is LFM later on. Like I don't know, interference contrast in the optical microscope. That it will not show you anything in the grain, but when you go from one grain to another grain, there's a discontinuity, and you will see a very high phase shift available. So that is done. So a lot of good papers those days have come out. I had a good work on that, along with the Saurashtra University as well. And then some of the good work again with the IIT Mumbai, Professor Major and this Gupta. They used to make, you see the sample doesn't very appealing at all. This is a lagmule blocked film of a cadmium arachitate. Cadmium arachitate has a very beautiful hydrophilic stem and a hydrophobic head, like a lotus flower. The flower don't like the water, so it swims. The stem likes the water, it is. So if you keep all the lotus fruits, go and apply a small pressure from outside, all the lotus beads will come and self-assemble in a hexagonal lattice. Same way it has happened here. The people were not believing. So I used to do a Fourier transform of a larger size image, about normally around 100 to 200 images. We do an average, and you see the very beautiful six spots in a Fourier representation. So hexagonal portion is slightly distorted hexagonal, could be confirmed by the direct space representation. You can see them. And then when you apply a small pressure and how they bend, they are soft material. Okay. So you can see it's like a missile. So they will have a bending and melting transitions, etc. That's what I'm trying to do. If I go on telling this would be a whole day, but you got very good work on this. And this is one of the very famous thesis of Prakash. A very good statement. It's a very soft material. Now, all these things so far I was talking about contact mode that has the highest form of resolution. You can able to see them. Now, there is a second mode of system is called tapping mode. Suppose you go to a small adhesive sample or a bacteria or a cell, biological cell, and this diamond tip exerts a very huge force. Even though you call them as a newtons, the force, nanonewtons to by nanometer is a force constant. So nano will catch as is equal to Newton per meter. It's like almost taking a big crowbar and hitting the sample. So damage of the AFM tip due to the very large atomic force at that particular small dimensions is a very huge. To avoid that, they invented a very beautiful mode called tapping mode. Some people say non-contact. I have shown the Van der Waals curve that instead of going to repulsive mode, go to an attractive mode. Just but attractive is not purely attractive. It has a repulsive component also, but more attractive portion. So if you allow it, it will go and stick to the sample. So we should not do that. Therefore, they indigenously did one more measurement. That is called you have a XYZ cantilever, other contact. You have to do one more something called piezo for the tip alone. So this oscillation piezo is a fourth piezo. You apply electric field. You apply electric field for this, but AC electric field. Then it will oscillate. Voltage will oscillate. Therefore, expansion will also oscillate. That means you contract, expand, contract, expand. So if you allow that one, the tip will also try to oscillate like this. And if you are far away from the sample, far away, you are 10 Armstrong and above, you will see a very beautiful free oscillations. And if you go very nearer to the sample will start interacting with the tape. Therefore, it is getting damped. So you will see a damped oscillation. These two can be worked out. A lot of it is like a harmonic oscillator and a forced harmonic oscillator. So you can find out the resonance and quality factor, etc. I don't want to come to this now. But you want to know at least you will have a two components. One is called in phase and out of phase component. So one need a lock-in reduction, and using the lock-in reduction, all these derivations, one can able to see the three different modes will come into the system. One is that when you oscillate it, there is a frequency. You can keep the frequency constant, or you can have amplitude. You can keep the amplitude constant, or you have phase. So A sin omega t plus minus phi, simple equation. In that, what will happen? You have A amplitude, sin omega t fully as a phase, omega as a frequency. So you have three kind of modulations of your microscopy. You can keep frequency constant, measure other things, or keep amplitude constant, measure the frequency changes. Very powerful in MF form. That's what we do it here. The next page, I'm going to. This is a small piece of a magnetic the recording tape where you can see only grains and grain boundaries on the left side. But on the right side, you can see very beautiful periodic structures of magnetic domains. These magnetic domains are on and off states of your whatever way you're recording. How it happens, I'm just giving a small crude explanation. The tip is coated with a magnetic moment, and this magnetic layer is only about 5 nanometers, not very high. Therefore, almost like unidirectional domains, monodomains of them, assuming that they are all down. For example, if your sample, normally if there's a sample is magnetic, suppose somebody should study what is the Curie law and Curie-Weiss law. The Weiss contribution is to study how you get the magnetic domains. So even for a full ferromagnet, you can see that always there is an up domains. Next domain will be a down domain, 180-degree domain walls. In between, there is a domain wall called Kittel wall is available, where magnetization flips from up to down spins. Therefore, your magnetization will look like a step-like behavior. And if you move the samples over on this, then you can see that in the magnetization, there's an interesting thing. And there's a come to the domain was it nothing. Again, in the down domain, you will get a opposite direction, a reflection like this. It goes on. So if you have a feedback, the path of the cantilever will look like this. If you keep the path of the cantilever constant, the voltages will look like this. And whatever it happened, it tells you what happened to the sample. This is a very beautiful, powerful, at least at the order of 15 nanometer resolution, one can study. but a little bit of magnetism, a little bit of technical magnetism. You should need to know. People should know what is a domain, and in system, what are all available to steps to do. So then one more interesting things we had something called all effect. All effect, everyone knows about it. So instead of transverse voltage and apply magnetic field, you will get a longitudinal and against the transverse current also. So current is going in X direction, magnetic field in the Z direction. I get a voltage in the Y direction. It is very useful to find the charge carriers, whether it's a holes or electrons. So everyone knows about all coefficient, and this can be used. This effect can be used as a probe, and Rachna Lakani probably she's also giving a talk. So this is what the structure. The current is in the X direction, and then you can see that in Y direction you are measuring. X direction long-term resistivity, Y direction passive resistivity. It is very useful for your quantum Hall effect, etc. Classically also same thing, but magnetically is a direction. Then it is very beautiful two-dimensional micro chips are available where they are called micro Hall probes. You can use them to scan the sample, measures wherever the magnetic field is there, depending on the current will change. Therefore, it's very powerful local magnetometer. It's called scanning Hall probe magnetic. Dr. Rawat and Dr. Sinalakani both were working on that. And of course, the later stage, much complex machineries. This is what I was telling you, and the photograph is a multi-crore machine. And then you need at low temperatures and high magnetic field work and study this. They used to work on very complex thing. But I worked on there. This is also a very nice conducting too. There are two big systems at UGCD ACSR indoor, and then it's a very powerful for studying both conductivity, okay, and magnetoconductivity, and also the Hall effect locally. It's very powerful. So to explain for students, see, it is like it's a similar. If you have a simple part magnet, flux will be leakages. It's not a good for you. So keep magnetic key for one north south and south north. Then you can see that the other losses are not except top and bottom. But if you keep material, automatically minimizes its magnetic energy loss by making a clamp like 180-degree domains like this, and then there's a 45-degree domains. People want to learn. It's all discovered and explained by very nicely by Wiss. That want to very famously by Kittel. Kittel books in solid state is very famous. And that's why this domains wall is known as Kittel wall. So from up domain, down domain, it will not happen in the next atom. Assuming the atoms are there, atom dipoles. It will not happen if you suddenly want to flip. You need a large energy, but it flips over a period of lattice parameter. So it can be 10 atoms, it can be 20 atoms. Typically, it is about 100 atoms. Therefore, at least 50 to 100 nanometers will be the Kittel wall where the magnetization goes from up to down. And this only makes you a very beautiful concept. As long as you are in up domain, no change. As long as a down domain, no change. The moment you cross from one domain to another domain, huge magnetic contrast is available for your force. And that force is measured. I'm giving you an example. When the thickness of the sample, magnetic layers are copper films, one of our own experiments in our consortium at the time, is that if you have a thin films of that, okay, normally an isotope is perpendicular, and you can see very beautiful circular domains, very interesting circular domains. You can even a vortices you can see them, and then the thickness between them. These fringes, I will say, fringe width of this will be proportional to square root of thickness, and small scaling can be done, and very much more good work can be done. The moment you grow more and more higher and higher in thickness, the magnetization vector will come parallel to the film, and you get it is about 100 micron, very big image. Actually, you see, at first we thought it's a crack. It's not a crack. It's a large domain. Okay, large Kittel domain with a bow tie contrast. Bow tie contrast means the tie which you put is not a full tie, only near the neck you do. It's called bow tie. Small. It's like a butterfly. So you can see that there are 90-degree domains, and 180-degree is opposite. So dark domain, bright up and down. You can imagine, you can expect very interesting physics, technical magnetism can be done. And this is again is a beautiful nickel and it's a magnetism and the silicon dielectric combination like multi-fluoride composites. AFM don't show anything. Very beautiful because depending upon the SiO2 particles and nickel particles, they are dispersed. But because of this magnetism is get disturbed, you won't see a big domains like this. But instead of that, a percolating path. Because the path here is also percolating. If you keep a rat here and a cat here, cat you will never be able to catch because these domains are totally non-inclusive domains. Very interesting. This kind of spiral domains are very popular, especially in the very recent chronic excitations. You will see such kind of chiral magnets or conical or like there are a lot of better things. So it's a very interesting. This magnet, see, visualizing the magnetic domains. Of course, these domains will move and there will be a lot of noise and energy, work and mass and effect, etc. Many things are there, which I have no time to do that. But these are very interesting, at least to see and enjoy. These are all students of nuclear science. They were very good. Now they are all a faculty at IIT and NSC and so from many places. So I'm very proud to have worked with them. This is one example of our own work. Is optical microscopy in a shape memory alloys along the Martin-City transition. They are also magnetic. So, like your teeth implants, many of them are nickel titanium. The reason is that they remember the shape, and if a small heat is given, it will retain the shape. So damage will be less. So implants are now mostly made of shape memory alloys, more steel and all. So you can see that this small streak of here, the streak become more, and finally they become 180-degree domains and then go. So this domain formation along the cubic to tetrahedral transitions are very famous. There is a subdomains of that in the magnetism called these domains. So you can see all these things in an optical microscope by decorating an nanoparticles of cobalt. Sorry. Okay. So this is a very famous work of Sullivan, who is very famous on showing the magnetism in optical scales. You see Kittel book, earlier versions of the Kittel book, cover page shows you the magnetic domains, especially vortices of a superconductor by putting iron particles on that. Okay, that's how they discovered the vortices, also proving abricos over. Okay, at very low temperature. This is called bitrate decoration. It's a very famous. But we did it using our AFM. You can see this is simple polished specimen, but AFM shows a large domains like this and a subdomains. The large domains are called Martin-City domains because they undergoes to a tetrahedral to cubic transition. And they also undergoes a paramagnetic ferromagnetic temperature about 70 Kelvin. Therefore, 70 degrees centigrade. So we just slightly heating the sample while the sample is doing the scan in MFM. So all very complex measurements. They did it later on. That is why I acknowledge now. It is not possible. One small set of normally half an hour they will work for one sample, but we used to work for one particular sample of this nickel magnesium with women. It's about 1 month or 2 months to get a good data. And once you cross the paramagnetic state, loses the magnetism, no contrast. But you will see the material shows a beautiful deformation. This is called very interesting Martin-City deformation, and this is displacive transition condition. The optical also shows you like this after the transition how these domains will disappear. But these are all very interesting. What is shape memory? What is magnetic shape memory? How they changes, etc. Part of our study. This is one example to tell you block diagrams. If you are going from a only simple form of magnetism, you apply magnetic field for this, the spin is a down domain or some domain with 45 degrees angle or whatever. Only the spin should change. Material will not change. Here you can see the whole material shift in the direction of the magnet. Okay, that is why it's a very shape memory and its characterization in all resources, exothermic flow, etc. can be substantiated very interestingly. That's why what we do is that we work on trying to get these domains done. Just go and sit in one of the domains and try to change the temperature, measure the magnetic frequency, frequency of the cantilever, how it changes. That's become the force derivative, and these derivatives will obey a beautiful, very beautiful curve like 1 minus t by t c squared. That works for the cases of a critical exponent of a phase transition. So you can study the magnetic transition, coupled magnetic transition, how it goes. The TC can be estimated compared to magnetism. Something like a macroscopic measurement, something like a microscopic measurement of one single domain and study their properties. That's what my idea is to say that AFM is not just seeing things; it can also do that. And similar work has been done in magnetic force microscope as a function of magnetic field by Rawat groups. They are a much better mission. Now, come back. I'm not sure how much time I have, but the organizer can tell me 5 minutes. Organizer can tell me how much time I have, and then you can apply a force, large force, in the chamber. And so the force curve can be measured. Force divided by the area in which you are using the forces, and already original shape to whatever shape you have deformation or strain. Displacement is elastic modulus. This can be studied and taken. This is a very beautiful nano indentation portion of that. Example for one single nano rod, how hard it is. You can able to measurement even for
thin film where you can't make a indentation. Still, the force curves can be measured because the cantilever will bend and yield, and the hard surface is there. For example, you take a finger and go into your it will go inside the water. But if you put it in the table, your finger will bend. No? The bending of your cantilever will tell you how much hard your surface. And this has been done. Very interesting nanostructures we have done it. A lot of good papers have come. Then CDS is a photoconducting material. We used to do a small, this young people only did a very good photoelectric effect with a small diode, 10 rupees photodiodes and LEDs. We use it, get the current, you get a decay and all these things studied. Very interesting. What is important is that we have studied all these things into a lot of work. You apply not this whole the deduction system AFM is you use a small laser, there's a cantilever, there's a photo. If somebody has done in MSc lamp and scale arrangement of a galvanometer, how a small rotation of a coil is affected intervention. All these things have studied. People have studied where the grain boundary currents are going. That's what very important. One can study the IV characteristics of a single photoconducting dot. That's what I want to say. Okay. Then we had a very beautiful experiments to show you how the grain boundary conductivity can take place in the system. You see in this, there is a sub-band gap excitation. Why sub-band gap excitation comes out? This is not nothing to do with indirect band exciton. It is because the defects will produce states in the Fermi level. Therefore, the band gap activated state to a localized states will be a very small. Therefore, instead of something like 2.5 EV, even at 1.5, 1.2 EV conduction starts. So we can study this. That's why they do the grain boundaries, have a sub-band gap photosensitivity, etc. was studied in the system, and it was very good pictures. You can see how wet it is. You can do conducting air. So if you take one small nano rod or one small nano particle, you can see the shape, you can see the size, you can see its density, mechanical property, all these mechanical, how hard, how soft, etc. And you can study its magnetic property of the magnetism is there or not. Then you can study its electric property. You can study its magnetic property. Many things can be studied. Though now the microscopes are very high. So you can see conducting force microscope. Then you have, so STM is a mother of invention, scanning tunneling microscopy, then atomic force microscopy, then tapping mode for biological spectrum, then conducting mode, magnetic mode, a lot of things. I don't know now whether I have a time. This is something called polymers. We have studied something called using an electric field like magnetic field microscopy, electric field. This is a polymer surface, but when we apply from plus 4 to white volt minus 12 volt, how the electric field modifies this system. From here, you can able to calculate induced dipole moments. It's very useful for electric as well as the polymeric samples. Then we have studied a lot of bacterial situation. One example that we showed is a very beautiful 90-degree fractals of the E. coli and Staphylococcus. They are all, E. coli is a rod bacteria with 4 micron. Staphylococcus is like a coccus, like a grapes. It's only 0.7 micron. But ultimately they look like this. You put one inoculum, another inoculum, in between they don't go. They go only opposite direction. Who tells them to go? Because they come nearer, they will compete each other for the food. So they never try to diversify. No two bacteria will never interact with each other. They will not kill each other. They will go because they know very well if they come. This is called repulsive chemotaxis. I will tell you in a very other talk because already 5 o'clock. I don't know how much time we have, but we can see them 90-degree fractals. And over a period, we can study this fractal dimension. We used to predict these fractals, beautiful 90-degree fractals. And I have no time, even for a small bacterium, called how the bacteria colonizes, how the drug interaction takes place, why some drugs become resistant. Everything by seeing the morphology, we can predict at what concentration they will happen. It's all very nicely studied. We can take one bacteria, like a grapes, you sit in that, apply the pressure using a tip, you know, it's very strong. You can't kill it, a bacteria, by means of applying a pressure because it's about 22 atmosphere. In a gas cylinder exposed, it's only about 12 atmosphere. So 2 gas cylinders exposed will not be alive, no? But bacteria will still alive. They will not. The turbulent pressure is called. It's very, very beautiful, and it has a big role in understanding the biomechanics. So I will not go. We have deducted some of these bacteriophages called nanophages. This is how this bacteria tuberculosis is there. How we deduct with this. This is one beautiful example. One bacteria surrounded by macrophages. If you do it by a clinical technique, it will take around 15 days to 25 days to detect a proper mycobacterium. But then now with the AFM, we did it for 5 days. So it was a very, very interesting euphoria created at the time. So it's very interesting, and we did a lot of. Now the present AFM is very high. It's a multi-crore facility, not a single. People can see the atoms. They can see the magnetic spins of the atoms. They also see the spiral effect of this beautiful excitation called scremions. The future electronic or spintonics to motronics, it goes now called scremionics. So scremions are the beautiful low energy excitation. Gives you a binary logic, and that is going to be happen. The tip should be magnetic, and you should have a spin and you can measure the spins. This is what the aim, but you need a very low temperature of the order of 4 Kelvin and below a microscope should work. Okay. So with this conclusion, I thank the organizer and invite the questions and whatever. Okay. Thank you.
Okay, thank you, Dr. Ganesan.
Yeah.
Yeah.
I hope I'm in time.
So now, okay. So now we invite some questions from the audience.
Yeah.
If there are questions, please.
Probably it's the end of the day.
Rajesh Tiwari, I think you can ask questions.
Yeah. Hey, please.
Okay, if there are no questions.
Yes, yes. Okay, you can give us our numbers, mail, you can answer them. They can contact me.
Okay, fine. Hello.
Yes, sir.
Anybody? Anybody wants to speak?
Yes, sir.
Yeah, sure.
What? It depends on your normally, yeah. No. See, if I give an SCM talk, I will say SCM is superior. If I give TM, I will say TM is superior. This is a common idea. So SCM is good, but sample preparation is little bit less, and then sample should be reasonably polished if it is a bulk specimen. Otherwise, naturally inspired growth is very good. Okay, you don't need to do any, because if you touch a sample, you are spoiling the surface. Normally, the roughness should be at least of the order of sub micron size, because the lateral resolution is very high, like up to 10 micron, even 100 micron you can do, but 100 micron is very difficult because we have roughness, very heavy roughness. It will spoil your chips. So normally we go from 1 micron, slowly build up to 2 micron, 5 micron, 10 micron. More than 10 micron, normally you don't need if you are working on nanotechnology or okay. So it is very easier for you to understand, but you see that the domains probably 20 to 30 micron size scan very good because micron. But when you want to go below 100 nanometer, your sample needs to be reasonably later to the system, and this should be synchronous, etc. We should know some idea about this stuff. It is possible to work on one or but your working is very high. Okay.
Okay, Dr. Ganesan sir.
Yeah.
I have one basic question. There are fast scanning AFM available.
Yes, sir.
So is there any reduced resolution? We sacrifice the resolution there?
Which one?
There are fast scanning AFM are available.
Yes, sir.
Okay, so we are sacrificing resolution there?
No, it is not resolution. What happens? Something called temporal effects. Suppose your scanning is very slow, your temperature variations really affects atomic resolution. What they do is that they capture a large number of images and take an average of that.
Okay.
That's because we have now very beautiful. I told you now, we started working 256 by 256. Then it become 512 is very expensive. Now they are 1024 is very common. Nobody is even on that, and now up to more than 5000 by 5000 scans are available. So they all because of the FPGA and your memory.
Okay. Thank you, sir.
Yeah.
Okay, if there are no questions now, we end this session here. And I thank both the speakers.
Yeah.
And for the journey, Vigyan Yatra from astronomical unit to angstrom unit.
Yeah, right.
It was
Very
really
fantastic.
nice, both the talks, very excellent talks we had.
Yes.
So thank you very much, sir.
Yeah.
Dr. Vishal Joshi and Dr. Ganesan, sir.
Yes.
We heartily thank you, sir. Thank you very much.
Yes, sir. Thank you. All of you.
Now, Bharvi. Hello. Bharvi
Yes,
Hirpara.
yes, sir.
Over to Bharvi Hirpara.
Yeah. So, our keen and anxious attendees of today's Vigyan Yatra, a series of conference jointly organized by Department of Physics, Saurashtra University, Rajkot, Vigyan Gurjari, Gujarat Prant, and Gujarat Vigyan Sammelan, as well as GUJCOST, DST, Government of Gujarat. We all know science of today is the technology of tomorrow. We live in a society exquisitely dependent on science, and events like these help us to dive deeper into the ocean of scientific knowledge. Myself, Bharvi Herpura, research scholar, Department of Physics, hereby take an opportunity to thank our eminent speakers of the conference on behalf of the conveners, Professor Nikesh Shah, President Vigyan Gurjari, Professor P.N. Joshi, Secretary Vigyan Gurjari, event coordinators Professor K.B. Modi sir and Dr. Piyush Solanki sir. We often look at science as something we light and only a few people can learn, but today's learned scientist, Dr. Vishal Joshi sir, and a scientist at PRL Ahmedabad, and Dr. V. Ganesan, Dean, Medicaps University, and former director of UGC CSR Indore, have proved that notion wrong by explaining the perplexed concepts like black hole, analyzing material, in a very lucid way. I also thank Professor Hiren Joshi sir, the professor and former head of Department of Physics, Saurashtra University, for providing his valuable time and chairing today's session. The organizers would also like to express our deepest gratitude to Chief Patrons, Professor Nilambari, Madam, Honorable VC Sir, VC Madam, Saurashtra University, and Professor Chaitanya Joshi, President Vigyan Gurjari, patrons of the event, Professor GC Bhimani Sir, Dean of Science, Saurashtra University, Dr. Narottam Sahu, Honorable Advisor and Member, GUJCOST co-patrons, Dr. R.G. Parmar Sir, Patron, Registrar of Saurashtra University. We thank all of the dignitaries for their tremendous support and making this event super success. We have yet accomplished the first year and we are very thankful and look forward to the enthusiastic participation from all the audience for the next 9 days, for the next 8 days. And thank you. See you all tomorrow at 2:30 p.m. sharp. You are all requested to join between 2:15 p.m. to 2:30 p.m. for the ease of management and timely progression of the